Hi, so today we're going to talk about antennas, indoor connectivity, and the way how phones are working inside buildings. My name is Juha Lilja, I'm founder of StealthCase, and we are a company who is specialized in creating antenna technologies that can be integrated on glass. So this presentation is about comparing different solutions, and I'm going to go through two different solutions that are behaving in a different way. We're going to talk about what kind of markers we should be looking at when we want to estimate the end user experience. Many of you already know that new buildings can have lots of problems with phones. Phones are not working correctly. And the reason is that walls are attenuating signals. Concrete wall is poison for connectivity. Thick concrete walls don't allow signals to go through. Same is coated glass. It's attenuating the signal. And the performance of the link, the communication speed is directly dependent on the signal strength that the device is receiving. You can see an example there. That's a measurement that we made this year on real-life operational 5G network. You can see with the red bar how coated glass can really kill 5G connection speed. But we can actually recover the speed when we're using mobile-friendly glasses, so that's a good thing. And this is actually something that the glass industry can monetize, the solution. In this presentation, I'm comparing two different solutions. I'm going to concentrate on 3.5 gigahertz 5G frequency. That will be one of the most important 5G frequency bands that will be deployed. And why do we need mobile-friendly glass? The reason is we want to use our phones and wireless devices in buildings also in the future, in a way that they were designed to work. We have a couple of examples. Top right corner shows the simple example. So there's a phone inside a building. It tries to connect to a base station network located outside of the building. Wall kills the signal. The signal gets too weak when it enters indoors. But when we provide these passive RF apertures in building envelopes, like in the example shown below, we are able to reduce the attenuation in walls. We are getting recovery gain for the signal inside. This is a measurement that we've also made on 5G real operational network, showing how the connection speed is directly dependent on signal strength. And this is the important thing, because all wireless devices behave like this. There are no exceptions. 5G, 4G, 3G, IoT, and so on. So basically, when we or you attenuate signals with coated glass, the end user is operating on the bottom left corner of this kind of graph. But when the attenuation walls gets weaker, signals get stronger indoors, the signal is recovered closer to the top right corner, not reaching that completely. But when we lower the attenuation walls, we can get more speeds indoors and more reliable connections. This is what we studied. So basically, we can see three examples of metal walls with holes. On the left, that's a reference. Uncoated glass, basically just a hole in a wall, but you can call that as a solution if you wish. In the middle, so-called frequency-selective-surfaces. These kind of products are in the markets, and those are rushing to the market. So you will be seeing lots of those. The idea is to ablate, remove parts of the coating to reduce the attenuation of the glass. And so this cross-hatch pattern that is used here as an example is behaving as a low-pass filter for the signals. On the right, we are seeing something different. It's an antenna array, slot antenna arrays on glass coating. We can use the same fabrication method, but first of all, we see one big difference in the treating area of the glass. These two solutions in this study were designed to provide the same amount of total power through the glass. And I will show how different they may look, depending on how we look at this. This is a full wave simulation of showing how actually microwave energy propagates. On the left, you see a wall with a hole. On the right, you can see the same wall with the antenna. You see something completely different. This is how signal behaves when it goes through an open hole, through a window or frequency-selective surface. You can see all the energy is concentrated on that small spot with high intensity. On the right, you can see that the antenna can throw the signal sideways. So from the signal point of view, we are having two completely different scenarios, how we actually affect the propagation of the wave. You can imagine that being horizon, and there are base stations somewhere. We want to connect to those. The one thing is that if we want to compare this, so how can we actually compare? There's a traditional way to measure. We have this transmitting antenna, and a receiving antenna is usually placed on the other side, on the direct propagation ray, and that's all. They measure some traces and compare differences. If we would do the same here with the antenna and define that the difference that we see in traces would be attenuation, we would be completely wrong. Because you can see that the energy is not anymore going there where we want. We are measuring something else. Same thing. So we can say that these two work for any incident angle. You can see we are throwing the signal from the 45-degree angle. You can imagine the user moving inside a building. Both of these throw the signal through, but the energy is spread in a different way. So if we place one antenna there to receive something, we are not measuring intensity in that small space angle, solid angle. And if you imagine that we try to sample something three-dimensional with one single solid angle sampling, it's impossible to define what's happening because we don't have any senses for microwaves. Unless we really understand what happens, it's impossible to make direct conclusions. We really need to study structures first. And this is in real life, because in real life, windows have and the edges. The structure itself affects the way how signal propagates. So what we measure there is a combination of attenuation and directivity. We are talking about radiation patterns, like with antennas. We need to break the analysis into different cases, because first thing we need to do is to actually analyze the full power that we can get through an coated glass. I'm talking about three-dimensional power. We really need to characterize and integrate the entire three-dimensional space behind the glass, because we don't have any other options. This is the way how all phones, mobile phones, are being specified in the mobile phone industry, because we don't have any other options but to measure the three-dimensional behavior. Then we can talk about efficiency that is independent of radiation patterns. It's the second step to analyze intensity, where the signal actually goes. When we know these kind of things, we can actually design something. We can affect the way how signal propagates. So we are not, in many cases, we are not anymore talking about dummy holes in walls. We are actually affecting the way how signal is flowing. You can see the examples on the left. So if you imagine, if we push 1 watt of microwave power through those glasses, in both cases, because these were designed to provide the same amount of power. Above, if we divide that energy into small area, we will have high intensity there. You have this there. And below, if we divide the same amount of energy into bigger solid angle, we will have lower intensity, but still 1 watt through the glass. But what we actually gain when we lower the intensity, we get better coverage. You can see there's a horizon, base stations outdoors. They are in the horizon. We don't know where those are. We want to maximize the probability of reaching multiple base stations. So this is something that we can actually gain by lowering the intensity and using beamforming to make really wide, more reliable connections. this is what we need to analyze. We actually need to look at the entire three-dimensional behavior. Because when we are using, let me stop again. What you first see here is top row shows the examples that we are comparing when the signal comes hitting the glass directly from the normal direction. The bottom row shows the cases where signal comes from the side, in this case from a 45-degree angle. The user is moving indoors. This is what happens outdoors for the signal, or for the scattering pattern through the glass. We see something different with the antennas. We are seeing that really wide beam, but when we are using so-called radar cross-section analysis, we are able to actually simulate the entire big geometries. These are computationally really heavy stuff. It needs lots of computing power to calculate this with all the details, but we need to do that, because unless we do that, we don't understand what we are measuring. So, open hole, the left one, float glass, and frequency-selective surface. They are really directive. Signal goes through, like through a pipe. Those actually we are able, we can measure using the traditional way to measure if we place the receiving antenna on that spot, because the radiation pattern is similar. We are not redirecting the signal in other directions, but if you use the same there, we are measuring also the drop in the intensity, because the signal is somewhere else. What we are looking here is a two-dimensional map over the horizon. Basically, we are talking about coverage map. You can see the horizon line slicing all of these pictures. On the left, you can see frequency-selective surface, and on the right, the antenna array. So basically, in the horizontal plane, 180 degrees goes from left to right. I computed the entire power that was sent to horizon with the frequency-selective surface, and analyzed how much of that power we are actually concentrating on that spot to the maximum beam, and it was 90%. Then I analyzed how much the same area contains power of the antenna. It was 26% only. So 70% of the power was sent somewhere else in the horizon. So it's actually clear that now when we want to measure with some single point sampling, we are not measuring actually the attenuation anymore. We are measuring the result of attenuation and directivity. The top row shows, once again, the thing when the signal comes hitting the glass directly, and the bottom row when the signal comes from the side. And it's quite cool to see that the antenna can actually remain the radiation pattern, the coverage. So it can provide really uniform field regardless of the user movement. Now, we measured those. We have an unequal chamber with a wall inside. We can measure glasses and different kind of construction supplies. Top left corner shows the case, how we measured here. So we have the glass, and we are measuring this directly through the glass. We have the receiving antenna there on the other side, using the traditional method. On the right, you can see simulations of the radiation patterns now on the horizontal plane. Now the scale is the same here. Actually, in the three-dimensional pictures, the scale wasn't the same, but here it is. So the red arrow shows where the signal comes from. Table here shows values, what we measured. First, raw antenna-to-antenna coupling results, and then the same comparison compared to what we measured with float glass. First of all, with frequency-selective surface, we got a number of -7 decibel. These are measured at signal point 3.5 gigahertz frequency. So -7 decibels. And we would say that the attenuation is 7 decibel, at least the transmission loss. When we look at the antennas, we are getting a value of -17. We are not able to say that attenuation of the antenna is 10 decibel higher, because the power is somewhere else. But the intensity is dropped in that direction. What we measure is that difference in that maximum peak affected by the radiation patterns. That's the only thing what we are actually measuring here. The agreement is quite nice between simulations and measurements. And this is when we measure the direct ray, okay? And what happens if we look behind the corner? So now the signal, once again, comes hitting the glass directly, but we just measure the radiation behind the corner, like this. The situation is reversed. Now the antenna is giving 10 decibel higher values. Once again, we are not able to say that the antenna is 10 decibels more effective if we are talking about attenuation, but it's, the radiation pattern is different. One actually cool thing in this is that when we compare the value, what we got with antennas, against the value what we got with float glass, we're actually seeing a positive sign. Antenna is throwing more power behind the corner than an open hole. This is something that we can get with, we can design something new. This is not just a dummy hole. We are able to really affect the coverage, how the structure is behaving. So, yeah, once again, the three-dimensional efficiency of these two structures was the same, but we can see plus minus 10 decibel fluctuations in lab measurements depending on what we actually measure and how we measure. And then we also measured that in the field. So that's a really cool startup chamber, that metal chamber. It's fully enclosed metal chamber. We are using that for measuring how much we are able to actually get power through that glass. The chamber itself is covered from the inside with microwave absorbers, so there are no reflections inside. So it's working like a big open space. And in that location, we replaced the glass with the different prototypes, and we were observing what kind of signals we are getting through the glass. So we are measuring only glass this time. We have a commercial 5G wireless receiver inside that chamber. And in the same location, we replaced the glasses. This is what we saw. Both of those solutions gave 9 decibel attenuation for the signal. So these are numbers what the commercial terminal was seeing. So they were designed to provide the same power for the three-dimensional space, and they agree quite nicely with real-life measurements what devices are seeing. We don't see here fluctuations of 10 decibels. And these both work in the field. They both gave about 200 megabits per second in that location, because that depends, the speed that we get in the field depends on the signal strength, like I mentioned in the beginning. And with low glass, the attenuation was actually almost 30 decibels. That's a lot. And the speed dropped to about 5 megabits per second. So that's a 5G connection, not so fast. But to summarize, so when we are building buildings of the future, we need to think about indoor connectivity while we are building, because any attempt to fix the connections afterwards are much more expensive. It's actually quite cost efficient to make a mass production scale mobile friendly glasses that can make the connections much better indoors. We're talking about 5G, 4G, 3G, IoT devices, all wireless devices. Different solutions are in the markets and are rushing to the markets, but it's good to understand that there will be lots of trace-to-trace comparisons, but I would say that in many cases, it's not that straightforward, actually, what is being compared. Personally, I don't really like that much of comparing traces unless I really know what is being measured. I'm talking about the effect of the radiation patterns. Are these the same? What are we measuring power? So we have seen that when we actually characterize the entire three-dimensional power, what we get power through the glass, we are getting quite nice agreement between predictions and real-life performance. And this, yeah, with this three-dimensional analysis. Two-dimensional mapping is something that we can use in advantage to design some features and how we want to control the flow in different directions and things like that. And so this is something that the glass industry can actually monetize this solution in a passive way with passive mass production scale products. Right. Thank you.
Now we have time for questions from the audience. Anybody? Yes. Mike.
Thank you, very nice presentation. Regarding this antenna which is installed, which is put on the glass, you should have different patterns of this antenna, different designs, or just this one we saw in the photo in the slide.
The antennas here are for educational purpose. If you want to see real antennas, those are actually visible at stand number 18, where we have windows with antennas. Antenna patterns are designed for different frequency ranges, but usually, of course, we want to throw all the signals at all reasonable frequencies through the glass. Changing the pattern is something that can be used in an advantage, because if you, for example, want to block Wi-Fi signals going through the glass, we are able to design antennas that allow other signals to go through, but they will not completely kill Wi-Fi, but attenuate that a lot. If you, for example, imagine having an office building, you don't many times want to throw Wi-Fi signals to the street. You want to keep those inside the building. These kind of things can be done by using antenna design, because we have slot antennas. Those can be just designed by changing the shape and orientation and things like that.
Thank you.
Thank you.
Any other questions?
Thanks for the interesting talk. I'm curious about this, the total power going through the glass efficiency. Which result proves that the FSS and the slot antenna gives us the same efficiency?
Excuse me?
Which result shows that the efficiency is the same for the FSS and then the slot antennas?
Those are actually in the manuscript. I want to keep this really simple. It's in the manuscript. But
how did we measure that? How did we quantify that?
So here the analysis is done with CST Microwave Studio. We are integrating the entire space. We're using. Okay, you understand.
I understood. Thanks.
Okay, yes.
Further questions? Unless there are no further questions. Thank you, Juha.
Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.